All right, well, welcome back. So in this video, we're actually going to be doubling back on a few of those topics that we saw back in Unit 3, and we're going to slowly introduce a little bit of notation as well as some key concepts that we're going to use as we jump into this world of ciphers and prime numbers as well as a little bit of encryption. So actually, to double back on this kind of formally, we're actually going to bring back one of these examples that we saw back in Unit 3, and that's this question of I'm given a whole bunch of different numbers, and I want to determine what their remainders are when I divide these things by the same exact number. So in this case, I was looking at the numbers 14, 54, 179, as well as negative 36. And I know that if I divide these things by a 5, they're all going to kick out the exact same remainder. In this case, they all kick out a remainder of 4. So what ends up happening is that if I phrase this in the world of modular arithmetic, I know that I'm going to say that 14 is going to be congruent to a 4 mod 5. Likewise, I know that 54 is also congruent to 4 mod 5. 179 is as well as negative 36. So these four numbers, even though they look very different, kind of in the classic just integer setting, I know that if I look at these things in the mod 5 setting, they're all going to look the exact same. And what ends up happening is that these numbers are in a sense going to behave in a very similar fashion. So what I want to do is I want to take this notion of being the same and lump these things all into one set. And the name of the set is going to be referred to as a congruence class. So that's all this is going to be a somewhat formal looking notation, but all I'm doing in this case is I'm taking all of these numbers that happen to be congruent to 4 mod 5 and putting them all in one really big set. So the notation for this is somewhat unfortunate, and you're going to see in a little bit that the notation becomes really clunky, and at some point in time we just drop some of the notation because it's kind of awkward to have to write these brackets over and over and over and over again. But for right now, we're going to at least look at this from a kind of somewhat more formal setting, and then when it actually goes to the application side of things, we drop some of the formality. Okay, so in this case, what's going to happen is I'm going to be looking at this collection of objects that are all going to be congruent to 4 modulo 5. So what I'm going to do in this case is I'm going to define this set of 4 in a bracket, and there's going to be a little subscript of a 5. So the 4 is what these things are going to be congruent to. That little subscript is going to be the world that I'm actually living in. So in this situation, it's going to be this set, which is going to be a collection of random integers. So it's going to be all of these x's that happen to live in this kind of collection of integers, and they're going to have this special property that's going to say that x has to be congruent to, in this case, a 4 modulo 5. So that's all it's saying up above, is that I'm going to have this little a in a bracket, which is exactly what my thing is going to be congruent to, and that little subscript of an n is actually telling me what world am I actually living in. So in this case, it's a kind of somewhat clunky formal definition of this thing. If I actually wanted to write out the elements that are in this thing, I could easily at least kind of create a little set and kind of say, okay, you get the idea, and we keep on going from there. So we know that the number 4 is going to be in this set because 4 is most certainly congruent to 4 modulo 5. We know that if we add 5 to this thing, I'm not going to change the remainder at all. So I can go from 4 up to a 9, let's say. I could also add another 5 to this thing, and I could see that I would jump up to, let's say, a 14. I could add another 5, and I'd go up to a 19. I know a few other numbers that actually happen to be congruent to 4 mod 5. We found 2 of them, actually. We know that 54 and 179 are also going to be in this camp. So I'm going to have up to, let's say, a 54. I can cruise all the way up to a 179, and this list actually doesn't end. It just keeps on going on and on and on and on. So that's what we know what happens on the positive side. We know that it's going to kind of dive down to the negative side as well. I could take this 4 and I could subtract a 5 from it, which is going to kick out a negative 1. I could subtract off another 5, bringing me down to a negative 6, and then I could keep on going in the negative direction. We know that we're going to hit a negative 36 at some point in time, so I'm going to add a negative 36 to that list as well. And then it's going to keep on going on and on and on from there. So in this case, we end up with this gigantic infinite list. But all of the elements in this list have that really special property that they're going to be congruent to a 4 modulo 5. So in this case, you see that any element that you grab out of this thing, I know that if I look at it in the mod 5 setting, it's going to kick out a 4. What's nice about this is that I could do the exact same thing not only for a 4, but I could look at, let's say, all of those things that are congruent to 3. As well as all those things that are congruent to 2, those things that are going to be congruent to 1, as well as all those things that are going to be congruent to 0. So rather than actually having to handwrite all these things, I'm going to jump in time and actually have the nice typed out version of all of these things so we can see all 5 of these congruence classes coming into play. So in this case, I have this 4 sub 5, which is going to be this collection of all of these things that are congruent to 4 mod 5. I have this 3 sub 5, which is going to be this set of all these integers that are congruent to 3 mod 5. The same thing with the 2. They're all the things that are congruent to 2. The 1 is going to be everything that's congruent to 1. And the 0 is actually going to be all those things that are congruent to 0 mod 5. Which in this case, if you actually look at this, that set at the very bottom is actually a little bit easier to describe as simply these multiples of 5. Because we know that's exactly what it means to be congruent to 0 mod 5, is that you're actually going to be some nice multiple of 5. And that's exactly what's happening in this case. If you were to grab any of those elements out of that bottom list, you can see that if you look at those things modulo 5, or if you try to divide by 5, you're always going to be either kicking out a 0, or you're going to have a remainder of 0. So in this case, you're always going to have a remainder of 1. Here you're going to have a remainder of 2, a remainder of 3, and a remainder of 4. Right, so to finish off this kind of discussion about this congruence classes, I want to just slowly take this idea of this mod 5 example and look at it in a little bit more generalized notation. So what's going to happen in this case is I'm going to use this example of this mod 5 as our nice basis example. What's going to happen in this case is that all of these nice properties that actually exist in the mod 5 setting are going to exist anytime I do this kind of nice modular arithmetic modulo some nice prime number. So the first example we're going to look at is this idea of, is there any overlap between these sets? So the idea is that I can look at this number 19. So it's up in this kind of set of all these elements that are going to be congruent to 4 mod 5, because I know that if I take 19 and divide it by a 5, it's going to kick out a remainder of a 4. The question is that 19 going to exist in any one of those other sets? And hopefully you can see that that answer is going to be no pretty quickly, because I know that 19 is going to be congruent to a 4 mod 5, which is going to say that it's not congruent to 3, it's not congruent to 2, it's not congruent to 1, and it's obviously not divisible by a 5, so I know that it's not going to be congruent to 0 mod 5. So I know that that number 19 is going to live in that first congruence class. That is this collection of things that are going to be congruent to 4 mod 5, and it's not going to live in any of the other 4. And you could do that with any element you'd grab out of this thing. The same thing if I chose this number 12. Well, I know that it's going to live in this congruence class of 2 modulo 5, and it's not going to be in any of the other ones, because I know what its remainder is. It's a 2, therefore it's not a 0, it's not a 1, it's not a 3, and it's not a 4. So the fancy way to say what's actually happening in that case is that these 5 congruence classes, so 0, 1, 2, 3, and 4, are going to be what are referred to as pairwise disjoint. What this means that if you grab any 2 of those congruence classes, so in this case, I'm calling one of them the congruence class of A and the other one the congruence class of B, if I grab those 2 things, so in this case, if I look at this set of 4 mod 5 and the set of 3 mod 5, if I'm holding those 2 things, and if I compare the elements in those 2 lists, I'm not going to find anything that happens to be in both of those lists. So the set notation world kind of representation of that is going to be this idea of this bracket A intersected with this bracket B is going to be this empty set. So that's this fancy little symbol that we're going to see here. It looks like a 0 with a slash through it. So it's this idea that those 2 congruence classes don't share any elements. That is, these sets do not overlap. And it doesn't matter which 2 sets you end up grabbing. Anytime you grab 2 sets that are not the kind of same exact set, they're not going to have any overlap. And that's the really nice thing about these things, is that you have this modulo 5 setting and you end up kicking out these 5 different sets and none of them actually end up overlapping. So in this case, we can actually push this idea a little bit farther. So in this case, you could do this modulo any random number you'd want to. So that's exactly what this theorem is going to be saying. So if you're interested in pausing this and really seeing what's happening, you can pause it and see kind of the generalization of what's going on. All I'm going to care about is that you kind of understand how the overall idea of breaking these things up is going to work. I don't care so much about the formality of what's going to happen in some of these theorems. But the idea is that if you choose any random natural number, what's going to happen is that you can always do this modular arithmetic modulo that thing. So whether that number be 5 or 7 or 26 or whatever thing you want to. Well, you know that every single integer is going to live in its own congruence class, because I know that if I take 3 and if I reduce that thing modulo 5, it's still going to be a 3. So I know in all of these cases that I had before that 3 lived in the set, 2 lived in the set, 1 lives in the set, as well as 0, as well as 4. So that's all that first part of that theorem is saying, is that the number 3 is going to live in the congruence class of 3 modulo 5. So the second one is exactly this idea that you're either going to have 2 congruence classes that are equal, or they're not going to see each other at all. And that's the one that we were just describing up above. It's this idea that if I'm looking at all these objects that are congruent to 4 or congruent to 3 modulo 5, those 2 sets are perfectly disjoint. They're not going to intersect at all. So that's all that second bullet point is saying, is that you're either going to have congruence classes that are equal, or they're not going to see each other at all. And the last one is actually just saying, what does it mean for these congruence classes to be equal? So the idea is that if I look at the congruence class of 1 modulo 5, well, that's going to be the exact same thing as if I look at the congruence class of 6 modulo 5, because I know that actually 6 reduces down to a 1, so those sets are actually going to be equal. We typically like to work with the smallest little number that we can see, which is why I'm always looking at this idea of 0, 1, 2, 3, and 4. I don't really want to think about 5 or 6 or 7 because you could just reduce that thing right away, and it's going to be easier to work with that nice kind of smallest remainder that you can work with. So that's really all that third one is saying, is that if you look at this congruence class of 1 modulo 5, it's going to be the exact same as 6 modulo 5, also the exact same as 11 modulo 5, because all of those things we're going to reduce down to a 1. So in that case, you might as well choose the smallest positive number you can. It just makes your computation a little bit easier.